This
Recording.
conference will now be recorded.
Okay, good morning. So we had started with ray optics. As you know, ray optics means it has different like geometrical optics. So we use a lot of geometry, knowledge of geometry to analyze various phenomena which will be discussed here. So today we are going to learn, see, in atmospheric refraction, many splendid happens. Okay, many splendid phenomena happens in our nature due to atmospheric refraction. We'll take a few examples of that, and before that we'll learn another interesting thing, that is apparent depth. You might be thinking, what is this? So this apparent depth, if I have a clean water tank, okay, very clean water, if I just drop a 5 rupee tank and just drop a 10 rupees coin or 10 rupees coin and ask you to, at a single hit attempt, might be little, it might be difficult. Might to just little bit difficult get it at a single chance. Why? To refraction, the height of the coin will not be exactly what you see. Okay, and coin will be seen little bit raised. Okay, see, due to okay now. Okay, so I think, Deepa, are you able to hear me? I just saw a message that audio connection gone off. Now I think now it is all right. So please let me know if you don't hear, or you can just message me if there is some problem regarding
Working, sir.
sound and all. Okay. So the point is that, yeah, is that the coin will be seen, the image of the coin, virtual image of the coin will be seen at a certain height which is elevated from the actual height. So that height which we see from the top of the water surface is called apparent height, okay, or apparent depth. So that is the thing here, apparent depth. It is actually lesser than the real depth. So this is why sometime the bottom of the water tank will be raised. You might be thinking that the tank is shallower, okay, tank is shallower, but actually the depth may be much more than what
Sir, not here.
Sound is not there, Ram. Hello? Ram, sound is not there. Ram, unable to hear, Ram. Hello, Ram.
This conference will now be recorded.
Okay, so today we'll be discussing the atmospheric refraction and apparent depth. So these are all actually the effects of atmospheric refraction. Look, in the last two classes we had learned about refraction of light. So today we'll see how various splendid natural phenomena occurs due to atmospheric refractions. Okay, so first let us discuss what is apparent depth. Okay, so first we'll start with apparent depth. So see, this thing is very much actually we are very much experienced with this phenomena because of this refraction. Apparent depth is occurring. We'll see. I'll just give you an example where we see this phenomena. Suppose you have a clear tank of water, and if I drop a 5 rupees coin and ask you to get it at a single attempt, okay, it will be difficult for you to just pick that coin up in a single attempt. Why? Because you will be seeing the coin little above than the actual depth. Coin may be there at the bottom of the tank, but you will see somewhere little bit raised. Okay, suppose here is the coin, but because of the refraction of light, you will see the coin over here. Okay, somewhere here. So suppose this is the water layer, this is the surface of the water. So from here, this depth you will see, but the actual depth is this one. Okay, coin is at the bottom of the tank, but you will see over here it is little bit raised. So this is why sometime the tanks or various places like the ponds are sometime, or many sources of water sometime will be appearing shallower, okay, because of this refraction. Let us now understand how it happens. So as I said, this is due to the phenomena of refraction, and we will be able to analyze this by using Snell's law. Okay, so here let me just define what is this real depth and what is apparent depth. The real depth is the depth or the actual depth, and apparent depth is that due to refraction you will actually see a virtual image of the object itself, and that is little bit elevated at elevated height. So that height will be little bit lesser than the actual height. So you can see this is the real depth or actual depth, and this is the apparent depth. You can see from here, this point is the image is forming here. You can see in this particular figure there is an object at this point O, and from the water surface, suppose A to O, here A to O is the actual depth, okay, actual depth or real depth, it is called real depth. And depth AI, this is called apparent depth. Why apparent depth? Because this is not the real depth. As I said, if I ask you to pick up a coin, you will not be able to pick it up at a single attempt, because you will see the coin here not exactly at this point O. So let us analyze how it happens. See, here already we have discussed this thing when suppose this is N2 medium and this is N1 medium, and refraction happens at the interface. Okay, interface. So in this case N1 is air. Look here in this air, and N2, or maybe I can just go in other way also. Okay, in this case the refraction is happening from N2, if it is N2 and this is N1. So N2 is the water here, and this is the air. So refraction is happening actually from denser medium to rarer medium. Look, if I have a ray, suppose I have an object over here, so light ray is just going here. So this is the angle of incidence, and upon refraction at the interface, since it is going from denser medium to rarer medium, so the ray will be going away from the normal. So this is the angle of refraction. So you look, if I just backtrace, if you trace the ray, this refracted ray, so you will find a position somewhere here. Okay, if you trace the ray. So similar thing happens over here. Because of this refraction, so the refraction happens at the interface. You look, it is here. So suppose there are two rays. One is directly refracting through point A on the surface. Another ray is getting refracted, getting incident at this point B, and it is refracted, and this is the BC is the refracted ray. So BC is the refracted ray, and incident ray is OB. Okay. Now look, after refraction, what happens? It goes away from the normal. Okay, so this, since this is I, this is also I. Okay, this is also I. So this is the angle of incidence, and this is the angle of refraction. Look, if you see from the above the surface of the water, you will see this refracted ray, and our eyes will see actually in the straight way behind this ray, behind this BC ray. We will not be able to see the actual path OB, rather we will see BI. Okay, we'll see, if you just backtrace it, you will reach over here and see another ray. As I said, it is refracting from OA, like OA to A prime. This way it is getting refracted, and these two rays, look, this one and the rays which I have just backtraced, BC, so they are intersecting at this point I. I'll just clean it. Maybe I'll clean everything now. You look, it is actually here. It is meeting here. So what will feel like the rays are actually coming from or diverging from this particular point I. Okay. So this is actually the virtual image of this object at O. Okay, this is how we'll be seeing the apparent depth rather than seeing the actual or real depth. Okay, so for the similar thing, for the similar thing, like because of this internet, because of this refraction itself, we'll see if you just if you dip a pencil or pen in a glass of water, it will look like bent at the interface. Okay, it will look like bent, somewhat bent at the interface. Okay, so this you can do with you just take a clean glass. Okay, and you look, it will look like this. Okay, sorry, so it will be okay. Anyway, you can just see this thing practically, do it at your home, and then you can see this thing because of the same problem in the sense same explanation, because of refraction from denser medium. Here refraction is happening while light traveling from denser medium to rarer medium. Okay, rarer medium. So we'll just prove this. Let us do a little bit of mathematics over here. Look, if we just consider at this point, this is the B. If I just consider this refracted ray for this itself. Look, if I write, see Snell's law, N1 sine I is equal to N2 sine R. Okay, so this is the Snell's law. So what is N1? Here in this case, N1 is Nw, or the refractive index of the water. Sine I is equal to N air sine R. Okay, so if I write Nw, that is the refractive index of the water. Suppose this is actually the refractive index of the air. Refractive index of the air. So that actually is taken as 1. So I can write sine R by sine I. Okay, I can write like this. Okay, so look now, sine I. So here this is the I can write sine I and sine R in terms of C R of C sine R means sine of this angle. I can write sine of AIB. Look, this angle is R again. Okay, so AIB, and sine I means it is sine of AOB. Okay, so now this itself we can write in terms of this triangle. Suppose AIB triangle, AIB, this triangle, and these are actually right angle triangle. You can see from here this is a 90-degree angle, and I can take another triangle AOB. So from these two triangle I can write, see AIB, I can write as AB over BI. Okay, BI, and this angle of incidence I can write. So AOB, sine of AOB can be written as AB over AI, sorry, AO. Okay, I'm sorry, this will be BO, because I am going from AOB, okay, triangle. So look, in this case, I'll just put in this equation, okay. So I have got NW, or the refractive index of the water, is equal to sine R by sine R. I have to write this one. So AB by BI, and sine I can be written as AB over BO. So this AB goes off, then you get BI over BO. Okay, BI over BO. Now we have to make a little bit of approximation according to our eyes. See, human eyes, the eyeball is actually are very small in dimension. So very small in dimension. So if we want to see something, the rays has to be entering into our eyes, and that happens through our eyeball. So see, if we want to see this image, both this rays has to be, actually the rays have to be entering to our eyes, and that happens when this A and B points are very close to each other, very close to each other. I hope you have understood this point what I wanted to tell, but I'll repeat it again. So see, our eyeball is very small. If I want to see this phenomena of this apparent and real depth, etc., so both this A prime, A prime, and BC prime, BC rays, this both the refracted ray has to be entering into our eyes, and that happens only when this B and A, these 2 points, okay, 2 points are very close. Then only you will be able to see these two refracted rays together. So at this particular condition, what we can write? We can write Bi, okay, Bi is approximately AI, okay, and BO can be written as approximately AO. Okay, so from here we can write NW, or the refractive index of the water, refractive index of water, that is AI over AO, or I can write refractive index. Yes, so this is the thing. So or if you want to write actual depth over apparent depth, that will be here in this case 1 over refractive index of water. So in this case, you look, the refractive index of the water is, okay, just a minute. So in this sine R, okay, just I think it will be other way. So sine NW sine I, it is sine R into AR. So sine R over that. So sine R over sine I. So what I have written, AB sine I means AB over sine R means AB over AI. Sorry, sine, yes, so BI and this was sin I means AB over BI. Okay, BO, sorry, BO. So BO has to be, BO has to be here. Okay, I'll just clean it. There was a mistake in the calculation. I'll just repeat this thing from here, because actual depth over the apparent depth will give you the refractive index. Just a minute. There was a simple mistake over here. Just let us see here. NW means sin R over sin I. Okay, and look, sin I, if I just take this triangle AIB, this will come with sin R, so it will be AB over BI. Okay, and sin I will be AB over BO. Okay, so you will get here BO over BI. Okay, so and then that approximation BO is nothing but AO, so this will be actually the refractive index. So BO is nothing but AO at that approximation what I told earlier, and this BI will be equal to AI. Okay, so this will give you the formula actually. So refractive index is equal to the apparent depth, that is, sorry, real depth, that is the AO over apparent depth, that is AI. Okay, so this is the formula. Okay, I'll just write the formula finally. So finally the formula is refractive index is equal to real depth over apparent depth, or NW is equal to, here the real depth is actually AO and over AI. Okay, so this is the formula. Refractive index is equal to real depth over apparent depth. Okay, so using this formula we can solve some problems. Numerical problems will be coming in your exam, so you can use this formula to find out answer for that. So we'll just go to the next topic. See, the atmospheric refraction happens. So you might be thinking atmospheric refraction means what? And okay, so one more point here I just missed, I'll just mention over here. So sometime there will be a question, what is the normal shift? Okay, normal shift. Okay, normal shift means your real depth minus apparent depth. So this can be obtained if you know the thickness or the actual depth. Look, if I just take this out, 1 minus AI by AO. So this, from here you can find out, this is AO means the actual depth. If suppose that is D, if that is d, if you know that actual height, then you can find out what is the normal shift. So this is 1 by nw. So from here, using this formula, you can find out what is the normal shift or the position. From here itself, you can find out the position of the actual position of the object. Okay, if you know the real depth, you can find out the apparent depth. D prime is equal to d into 1 minus 1 by n, that is the refractive index of the medium, here in this case water. Now we'll see apparent position of sun is being seen due to atmospheric refraction. Okay, let me just explain this phenomena. So due to atmospheric refraction, the sun is visible before actual sunrise or after actual sunset. Okay, so you can see this is called horizon. Okay, this is called horizon. Actually sun is always there, but when the sun goes below the horizon, it will not be visible to the people who are on the earth planet. Okay, and when the sun is above this horizon, then people can see the sun from the earth surface. Okay, I'll just repeat it. So there is a line called horizon. Okay, you can see this is the line horizon. Okay, so if the sun is below this line horizon, below the horizon, then we say sunset. And when the sun comes above this horizon, then we say sunrise. It is actually sunrise when it comes above this horizon, and when it goes below the horizon, it is called sunset. In principle, when sun goes above the horizon, then only we should see the light from sun. And as soon as the sun goes below the horizon or sunset is happening, we should not see any light. But you know, before sunrise, before sun rises, 2 minutes before sunrise, we can see the sun. 2 minutes before. Okay, and at the same time, when the sun set happens after sunset, even 2 minutes, till 2 minutes, we can see the sun. So why it happens? Because of atmospheric refraction. We'll now explain why and how this happens. As I said, it is due to atmospheric refraction. Okay, so how atmospheric refraction happens, as you know, if suppose this is earth surface, okay, as you go above and above up to few kilometers, there is actually air, sorry, atmosphere. Atmosphere means various gases or air, and air contains nitrogen, oxygen, some water droplets, etc. are there, and various other gases, carbon dioxide in little proportion. Okay, you know the combination of air, right? So as you go from as you go up from the earth surface, the air becomes denser and denser and denser. Okay, optically denser, as well as materially denser also. Okay, so as you go higher and higher altitude or height, density of the atmosphere increases, hence the refractive index. Suppose this layer has N1, this has N2, this has N3, like that. As you go higher and higher, the refractive index actually goes higher and higher. Okay, it becomes greater and greater. So this is the thing happening. That means, there are mediums. If you have two or multiple medium and refractive index is same, then there is no question of refraction. But in the atmosphere, how refraction happens? Because of the change in the density, refractive index also changes for individual layers from from one another. Look here, this is N1, this is N2, this is N3, like that. Refractive index changes, and how it changes? It increases as you go higher and higher altitude. Okay, so now what happens? Okay, I think actually it is in the reverse way. Just a minute. It is in the reverse way. Refractive index decreases actually. Okay, refractive index is more near the Earth surface. This sequence is this one. Okay, the as you go higher and higher, refractive index becomes lower and lower. Okay, refractive index of the air layers decreases. That means here it is, suppose 1.3 or something like that, then it will be 1.1, 1 or lesser than that. Okay, so it will be like that. So in this case, when you see the sun is actually below the horizon, but its light actually goes up to the earth surface, up to the earth surface. And when the light is going from, when light travels from denser medium to rarer medium, then as I said, suppose this is rarer medium, this is rarer, this is N1 and this is N2, and here N1 is less than N2. That means the light of the sun, as I told, the refractive index of the higher altitude air layer will be lesser than the lower altitude. So in that case, the refracted ray always will be bending towards the normal. Okay, the refracted ray always bends towards the normal, and because of that, what happens, as it goes near the normal, it will, in another case, it will just go like this. Again it will go like, there are many layers, right? So it will be bending all the way in each layer, and upon bending in such way, when the light rays, you can see from here, when a person on the earth surface sees this ray, sunlight from the sun, it is actually bent like anything, and our eyes always follow the straight path. Okay, our eyes always follow the straight path. So it will see, like, we will see the path in which the light is coming at this particular place itself. We don't backtrace and come here. We'll see the light. See, if the light is coming, even light is coming like this, So we'll see in this way. Okay, we'll see just like this. So sun is coming from here, but we'll see because we are here. Okay, we are here. We see from here. So light, even though light is coming from here, because of this refraction, but our eyes will see the path straight away. So sun will be appeared here. Okay, so sun will appear over here to our eyes. Actually, this is not the actual sun. This is the virtual image we'll see because of this refraction. And similar things happens when sunset happens. Okay, we'll see still the sun is there above the horizon because of this atmospheric refraction. All right, so this is about apparent position or shifted position of the sun due to this atmospheric refraction. So this sequence you should remember. There was like in the beginning I had this confusion. So look, this is, if this is the earth surface, I'll just repeat it because in the beginning we had a confusion. So near the earth surface, if this is N1, this is N2, this is N3, this is N4, like that it goes above. So in the higher altitude, density of the air and refractive index both actually will be decreasing. Okay, both the density and the refractive index. So that means if refractive index near the earth surface is greater than the the next layer, and it will be going like this. Okay, refractive index will be decreasing as you go higher and higher altitude. Okay, so this thing you should remember. That's why when sun rays come from the sun, they have to travel a lot, like far distance, and when it reaches to our eyes, it is like each and every time it is actually bending towards the normal, and eventually the sun ray which comes to our eye will be really bent like anything, but our eyes will actually follow the straight path alone. That's why even though the sun is actually below the horizon, but we'll see above the horizon. So this says this actually the apparent shift happens by 0.5 degree almost. Okay, 0.5 degree, and because of that we'll see the sun 2 minutes before, or we'll see even after 2 minutes of the sunset. Okay, after 2 minutes over also we'll see the sun, okay, above the horizon. So that's why each day will be actually having 2 minutes extra, sorry, 4 minutes extra time. Like we should see 20, actually 12 hours, 12 hours. Okay, in the daytime you should see the sun 12 hours, but we'll see extra 4 minutes because of this refraction. Okay, so we'll go to the next topic. So the next topic is actually total internal reflection. Total internal reflection. Let me first tell you what is internal reflection, then we will go to total internal reflection. So what is internal reflection? See, when a ray of light goes from denser medium, suppose this is N2, this is N1, and refractive index of N2 is greater than, so medium 2, this is medium 1, this is medium 2. Okay, this is the interface, and refractive index of the medium 2 is greater than refractive index of medium 1. Then what happens? In general refraction, what happens, the ray, so this is rarer medium, So it goes away from the normal. Okay, this is R, this is I, and R is always greater than I in general. So internal reflection is that during this refraction, this kind of refraction, some part of light will be coming back to the medium to itself. Okay, it come back. So this is reflected. Part of the light will be reflected, and remaining part will be refracted. So this is refracted, and some part will be reflected back to the same medium. So this is called internal reflection. Okay, internal reflection when the light ray is getting refracted at the interface of two medium, and the light rays enters from denser medium to rarer medium. Some part of light will get reflected to the medium to itself, or to the denser medium itself. So this phenomenon is called as internal reflection. Now I'll tell you what is total internal reflection. Look here, what is total internal reflection? This is in short TIR. Okay, TIR, total internal reflection. So this happens in atmospheric refraction. Let us see this, which are there are getting refracted at various angle of incidence. You can see. So suppose there is an object inside the water, and you are seeing from the surface of the water. This is the air, and this is the water over here. As you can see, this is the denser medium. So some rays going directly, some parts directly refract to the, some part is getting, some here is actually reflected. This ray, as I said, and this is part is reflected back. This is internal reflection. Okay. Now, if you, okay, increase or change the angle of incidence, if you just increase the angle of incidence, okay, you just increase the vary. I can say vary also. You can increase refractance. Suppose the angle of incidence, then n triple prime is greater than m double prime, sorry, I double prime, then it is greater than I prime again. So if you just go like this, see, you know, like Snell's law, n1 sine I1, or I can write by sine I by sine r. Sine I by sine r is actually the refractive index of the blue. Okay, this is a constant quantity. The angle of incidence, if you change, refraction also changes. Since this is a constant quantity, refractive index of depend on the medium. Any medium is a does non constant quantity angle of refraction, because it is a constant quantity, does not depend on incidence or angle quantity or material property. Doesn't matter whatever angle incidence you take, take angle of incidence of refraction will change, that we have discussed. Now look, okay, what we are trying to mean over here, incidence. Increases, increase the angle of, then this angle of, as I said, you are going from denser medium, you are going from denser medium to rarer medium. The ray is actually going away from the normal that is there. Okay, but still this angle, if you increase this angle of incidence, so angle of look here, angle of refraction will be again increasing. So if you continue like this, you will see there will be a critical angle of incidence, which is named as IC. There will be a critical angle of incidence when your angle of refraction will be exactly 90 degree. Angle of refraction will be exactly degree. So that angle is called IC, which is critical angle. Okay. So what is the critical angle of incidence? The critical angle of incidence is that angle of incidence which angle of refraction is 90 degree. So when this happens, increase further that IC, suppose this is IC, if you increase the angle of incidence further IC or greater than IC, look this is the fourth place. So this the critical angle when the angle of refraction is actually 90 degree. But if you go beyond that, look here in this figure, if you go beyond that, then there will be no refracted ray. There is no refracted ray. What will be there? There will be reflected ray. That means the ray which is having angle of incidence greater than IC critical angle, the ray will be totally internally reflected. That means, see, in normal cases there will be some internal reflection. That means some ray will be reflected back to the medium 2, in this case medium water. But when you have the angle of incidence greater than the angle angle of critical incidence, then the refracted ray will not be there. The ray will be totally reflected back to the same medium. This is called total internal reflection. And see, in short it is written as TIR, sometime TIR, internal reflection. So look, this is the totally internally reflected light. Okay, totally reflected light. So even in normal reflection there will be some refraction at least, but this is the case where the light actually gets reflected totally means there will be no refraction. In total internal reflection there is no refraction. Okay, no refraction. The whole light will be actually reflected back to the same medium. Okay, so this is called total internal reflection. So angle of incidence, see there, so I'll just, there are few definitions. So what is angle of critical angle? So angle of incidence in the denser medium for which the angle of refraction in the rarer medium is 90 degree is called the angle of incidence. Okay, that is denoted by IC. And what is total internal reflection? So if you write in terms of like definition or in a nice language, the phenomenon in which, I'll write, the phenomenon in which a ray traveling from a denser medium to okay, just traveling at an angle. Okay, traveling at an angle of incidence greater than the critical angle from denser medium to a to a rarer medium is totally reflected back into the denser medium is called total internal reflection, TIR. Okay, so this is total internal reflection. Now we'll see few things here in the total internal reflection. So look, if I just, so this phenomena is actually is seen in atmosphere in various places. We'll see one or two examples for that. And this total internal reflection, this concept will be used in many places. So I'll write Snell's law, N1 sin I is equal to N2 sin R. So suppose my angle of incidence is exactly the angle of critical angle of incidence, then this will be sine 90 degree, R will be sine 90 degree, so sine R will be sine 90 degree obviously. So now look, what you get is sine IC is equal to N2 by N1, sometime it is written as N21, okay. And if I want to write sine IC, so if you want to write what is the refractive index of, see this is the denser medium N1 and this is the rarer medium N2. Suppose the denser medium is water, denser medium here N1 is water, okay, water, that means I'll write NW and N2 is the air, okay, so which has refractive index of 1. So what you get is sine IC is equal to 1 by NW, okay, 1 by NW. That means refractive index of the denser medium is inversely proportional to the angle of sine of angle of critical sine of angle of critical incidence. I'll just write it down, just a minute. So what we get here is that will be 1 over sine IC, okay. Sometime you will be asked numerical problem from this particular formula, okay. Sometime you may be asked what is the angle of critical incidence. So if you want to find out this IC, then what you have to do, sine inverse 1 over the refractive index, okay, like that you have to find out. So now we'll just get one incidence, that is the formation of mirage. I'll just go another 5 minutes and then stop the class. So see, in the atmosphere, because of total internal reflection, one more important thing we see in the atmosphere, that is actually generally seen in desert. Okay, in desert, mirage in the desert. So how it happens? This is again because of total internal reflection. Okay, so how it happens? So suppose there is a tree far off in the desert from a person here, if you can see here. Okay, now there are actually, see, if I just draw some layers like this, these are layers of atmosphere or air layers. Okay, air layers. So what happens? The light rays which are entering to the eyes of the person in the desert, actually not directly coming from, they are not directly going in the straight way to the eyes of the person or human being, so or maybe anything. So how it goes? It goes in a totally bent path, you can see from here in this figure. So actually it creates an optical illusion. This creates an optical illusion that there might be some water, because of which you are seeing reflection on the ground. Okay, so the actual tree is here somewhere, but you will see some reflection of the tree on the ground. Okay, so because of the warm air, so this happens in the hot sun, hot summer. In normal places, in hot summer or maybe in the desert, it happens generally. So when in the due to hotness of the air gets rarer, and as you go from, see, if it is medium 1, like layer 1, layer 2, layer 3, layer 4, etc., like that goes. So the layer near to the like the eyes of the man is actually cold air compared to the air near the earth surface. Okay, so the refractive index, you look, refractive index in this case will be, see, this is actually rare. So refractive index of this medium, if this is like this, so refractive index of the medium 1 will be lesser than the medium 2, and even it is lesser than medium 3. So the light rays which are actually going from here to here, so every time the light rays, it is actually bending towards the normal. Okay, because of this refraction from denser to rarer medium, and when it goes ultimately to the human eyes, it is totally bent like this, and as I said, our eyes follow the path of these rays only. So, and in the straight way back to this point. Okay, and we will be able to see an image of this actual tree over here. Okay, image we can see, but how do we feel like water? Because of the air blow, air will be flowing, so there will be temperature fluctuation. Because of temperature fluctuation, the refractive index of each medium, each layer will fluctuate, and because of that fluctuation, the position of the image will be actually fluctuating. Okay, like in the water, see in the water, like water surface of your pond, sometime you see the image is actually moving or it is shifting. Okay, exactly what happens on the water surface we see on the ground or on the sand of the desert. And sometime in very hot summer we see this kind of illusion even in our normal places, on the roads also. Okay, so this is happening because of total internal reflection. Okay, this happens because of total internal reflection. So I'll stop it here. Today we'll actually here these are simply phenomena, and you have to read and find out the explanation how it happens. So there are few more things which we'll just discuss on the next day. The most important application of this internal total internal reflection is this optical fibers, which I'll discuss in the next class. And then we'll move on to the refraction by lens. And obviously before I go to the next topic, I'll just tell you or discuss few numerical examples on total internal reflection. There are many good many good numerical problems which we'll discuss in the next class, and then we'll move forward for lenses and refraction in the spherical lens, etc. Okay, so we'll stop it here. So bye for today.